Hi, my name is Matt Orson. I'm the director of our system architecture group here at Rambus Security. Today, I'm going to discuss our silicon provisioning product line. I'll describe what we have today, and I'll talk about how we are evolving this product into a system that can secure an entire supply chain. Our presentation is broken into three parts. I'm going to start with an overview of the kind of equipment we have deployed today and what it all does. Then I'm going to move on to talk about use cases. Use cases are the fundamental building block of our provisioning story. They are the actual provisioning activity, and I'm going to talk about how those work and the kinds of use cases they're currently supported. And I'll wrap up talking about what we're working on now, which is extending all of those systems into a full supply chain security product. We can divide our provisioning story into three buckets: identity assurance, device lifecycle management, and supply chain security. Identity assurance is the original focus of our product and really the focus of most provisioning products. It's essentially a system to securely create and distribute keys, certificates, and other information and store it in chips. A chip with non-volatile memory needs an identity. It needs an ID. It needs device unique keys. Provisioning systems supply that information to the chip. Our provisioning system was deployed at scale over 9 years ago. It's currently provisioning over 2 billion chips a year. To hit that kind of number, we were originally focused on high volume, low latency, and 24/7 reliability. And while that is still an important focus of our product, recent iterations have enhanced the product to handle high mix, low volume production. So we do a lot more in terms of fine-grained job control, things like that. But we still have that kind of low latency and high throughput that can allow us to do over 2 billion chips a year. The second bucket is device lifecycle management. About 4 years ago, we developed what we call our Cloud Key Management System, or KMS. KMS extends the security boundary of the factoring provisioning system to the cloud. By moving the security boundary out of the factory to a cloud-based system, we can extend it into the field and enable full lifecycle management of the product. This can be anything from rotating keys to replacing expired certificates to bricking a device that has become compromised in some way. To really make this work, factory systems and cloud systems have to be fully integrated so we can leverage that information that was created in the factory and put it selectively into the cloud and enable full lifecycle management. The third bucket is supply chain security, and it's our newest initiative. We're extending our cloud system, the KMS, to selectively share provisioning information across an entire supply chain. The current system is really focused on a single supplier managing devices like a chip from manufacturing all the way into the field. Our newer product, the supply chain security product, is going to extend that to cover multiple vendors and to assemblies of parts. So instead of tracking a single chip from the wafer to the field, we can track the chip as it's put on a board with other chips, and we can track the board as it's put into a box with other boards. And at the end, get a picture of the entire provenance and security position of the chip, of a board made of multiple chips, of a box made of multiple boards. Before I get into the details of this, I'm going to take a step back and describe the components that make up our provisioning infrastructure. You can see here that we have 3 tiers. I know there's 4 boxes there, but manufacturing and cloud, as you'll see in a minute, are really at the same tier, the provisioning tier. On the left, we start with the root server. The root server is the root of trust for all the keys that are going to end up in chips. So that first tier is the root of trust of the chips you're going to manufacture. So that thing is where we create netlist keys, where we create device unique keys, where we create unique device IDs. Anything that's going to be provisioned to that chip either originates on the root server or it's derived from a key that came from that root server, or it's secured by a key from that root server. That root server is, as the name implies, the root of the system. That is the most critical system component in terms of security. So our root server is air-gapped, no network connection. It allows multi-factor authentication. It allows quorum-based authentication, and our customers typically install it in a physically secure location with biometric controls. By securing that root server as much as possible, we secure the root of all of the keys that are going to end up in the chips. The next layer sits in the data center, and it's the control layer. The control layer is where the operator sits, and this is really the only component that has a sophisticated UI. So where the root server was probably operated by security personnel, the control center is handled by operations. Assets that are created on the root server are moved into the control center, and an operator on the control center can then distribute those to the factory or to the cloud. As I mentioned before, our new product has a lot of job control, so all of that happens here. You want to authorize the provisioning of 5,000 chips at a certain location on a certain day. That happens at the control center. You want to check the status of the systems that are running in the factory. You want to make sure all the hard drives are up. Any alerts like that, everything's going to roll back to the control center. Now, in this picture, I only show one manufacturing site, but you can have a large number of manufacturing sites all hanging off of the same control center where one operator can oversee the entire operation, know where all the inventory is, know everything that's happening down in the factory. So moving to the upper right, the manufacturing box, we're now at the actual provisioning tier. So at the manufacturing, we deploy typically a cluster of machines because, as I mentioned, high availability, high throughput is crucial. Those machines do not require any operator activity. They're all controlled by the control center, and that's where the provisioning happens. So all of these assets that were created all the way on the root server can travel all the way into the manufacturing site and be secured along that entire pipeline. In fact, as I'm going to show you later, we can create a secure relationship between the root server and the chip itself so that keys created in that secure facility on the root server are never in the clear, never visible by a human, and they're never in the clear until they're actually decrypted on the chip in a manufacturing site thousands of miles away. A lot of this is controlled by hardware security modules. Hardware security modules are discrete, tamper-proof units where the cryptographic operations happen. Every single one of these machines has a hardware security module, or HSM. So in the root server, when we created those keys, even the operators, even those 3 trusted security people that were in that room creating those keys can't actually see the keys. Those keys are kept secret all the way until they reach the chip. Finally, in that third tier in the provisioning, you'll see the cloud instance. I'm going to talk about this more later, but information from the root server travels to the cloud, and manufacturing information that can only be gathered at the point of provisioning is also transferred to the cloud. And together, that creates the foundation for secure connections to devices in the field. Our next section is all about use cases. As I mentioned before, use cases are really the fundamental building block of our provisioning activity. We provision a lot of different chips. You have a lot of different devices that need provisioning. Even one device at different life cycles might need a different provisioning activity, a different set of keys. In one case, you need to push a key. In another case, you need to extract a public key and create a certificate from it. That's why we built this as a platform for running use cases. Here are just a few examples of the over 150 use cases we have deployed today. Probably the most common thing we see is device personalization. I talked a little about this before. This is device IDs, manufacturer IDs, device unique IDs, shared keys, a single key that is going to be put across an entire class of devices. a CA root chain that can be used to verify certificates presented to the device. That kind of device-specific provisioning all comes under device personalization. The next most common use case we see is certificate support. This product can build pretty much any certificate you can imagine. We can do X509 standard-based certificates. We have provisioning cases where customers are doing custom certificates, which are basically a binary blob and a signature. What we found is that while in a perfect world, if you were building a certificate for a device where you're binding device keys to a device identity, the keys would be created on that device. But in the real world, we find that some devices are not capable of creating their own keys, or in manufacturing setting, it simply takes too long to create an RSA key pair or something like that. It takes just too long to create the keys. So the truth is that most of our customers don't use device-generated keys, even though that's fully supported. They use keys that are either generated by the crypto manager infrastructure itself, way back there on the root, or even keys that are imported by third parties. The point here is that in our generation of these certificates, we can get the keys from anywhere. We can get the data from pretty much anywhere. And I'm going to get into that a little more when I talk about the anatomy of use case and how that all works. One other thing under the certificate support, we also handle DICE. If you're not familiar with DICE, DICE was really deployed mostly on IoT, but is now moving very much into data centers and other locations. DICE is a way of generating keys and building certificates that proves the authenticity of a system, of a chip and a firmware running on that chip, like a bootloader or an operating system, of applications running in the operating system. So DICE is pretty common. We support DICE both from an authentication and a generation standpoint. The third use case I want to mention is featurization. Featurization is employed by our customers who want to control the number of SKUs. Rather than creating a lot of chips, most companies will create a smaller number of chips, of devices, and then they will do something to turn on or turn off capabilities. This reduces manufacturing costs, but if you do that really early in manufacturing, you still have a lot of SKUs, you still have a lot of inventory management. So what some of our customers are doing is they're postponing that featurization to later in the supply chain, and they're running secure vectors to turn those features on and turn those features off. This isn't terribly new. The point I wanted to really make here is that for that to work, there has to be secure auditing. Featurization is almost always tied to some monetizable event. Either that device got more expensive or it got less expensive based on the featurization vector that was just run. So there has to be secure logging coming all the way back from that factory provisioning, from that point of provisioning back into, in our case, the control center, so that you can verify and you can audit exactly what happened. And to be auditable, it needs to be cryptographically verifiable. That's what our system does. Activity that happens on the factory floor creates cryptographically verifiable audit records. That's how we can support featurization. Let's look at a couple of very specific use cases. This one is by far our most common use case. It also maps really well to our root of trust product, CMRT, in that we have really dialed in this use case for our root of trust. Our customers have dialed it in for their chips as well, but for our stuff, we have this stuff off the shelf. It's all pre-built. So in this example, netless keys are created on the root server. Those keys are created before the chip is manufactured. Those keys are created and exported from the root server in an encrypted form and then included in the RTL of the chip. Those netless keys are constants that will exist in the chip. By doing that early, by doing that as part of the manufacturing process, we have built trust between our entire CM infrastructure product and all of the chips that are coming off the line. We can then leverage that trust for the first touch provisioning. So as I show on the slide here, that root server later on, it can create class keys. By that, I mean keys that are shared across all of the chips. device unique IDs, device unique keys, the featureization vectors I mentioned earlier, pretty much anything that you might want to write to that chip can be secured with the netlist keys. So those things can be kept secret, taken all the way to the factory and provisioned down to the chip, and they will only be readable by the chip because those netlist keys will be used to decrypt it or to verify it or whatever is needed to make that transaction secure. So we have taken trust built into the silicon. We have leveraged it for the first provisioning activity. In our CMRT product, our root of trust, there's a way that you can disable the use of netlist keys if you choose to. A lot of our customers want to use those netlist keys early, but because they're constant, because they're the same across the entire product line, they only want to use them at those very early stages. So later, you can use any of these other keys that you have provisioned to the chip, the device unique keys or the shared class keys. So later activity can use those keys, and you can leave the netlist keys behind after that first touch. Our next example illustrates how we can leverage factory provisioning into that cloud system, the KMS. In this example, there's already been some kind of factory provisioning, and we're now going to put a new device unique key down on the chip. In this example, which is a real example we have running in the field, we don't control the device ID. In the one I'm thinking about, the device ID is an attribute of the chip based on location on the wafer, a random number, and a few other things that they put together to put a device ID together. So while we've created the keys over on that isolated root server, we don't know which chip they end up on. So what we do is we move those keys to the factory. We also move the keys to our key management system in the cloud. During factory provisioning, we gather the device information from the keys and we from the device, and we map it to those keys. So we get the device ID off of the chip and we map it to the keys. We move that information to KMS, and now when a device presents itself with its unique device ID, we already know which keys to use to secure communication. To make that work, you have to be able to trust that mapping. So the chip, in this case, creates a cryptographic value, which is a hash of its device IDs and the keys that are being provisioned. All that data, none of it's secret, it's all just hash, it's all just metadata, is transferred to the cloud, where the cloud server can verify it against the keys and get a rock solid binding between a device and the set of keys. Once you have that, when that device, that phone, that car, that factory equipment presents itself to the cloud server, we can authenticate the device with challenge response. We can do attestation based on device signatures or the DICE platform verification I mentioned earlier. We can do certificate generation, access control, pretty much anything. That's our factory to cloud provisioning use case. So how do we do all of this? As I mentioned before, we built a platform. We wanted a platform that could handle any use case that's thrown at us. So this is the architecture we've deployed. We break this down into the host system. These are Linux servers. They're 2U boxes. As I said before, they have hardware security modules or HSMs installed. So it's a Linux box with an HSM installed on it. And our use cases allow our customers to write custom code at the Linux layer and custom code inside the HSM. So honestly, most of the work is done in the HSM. The reason you put custom code in the Linux layer are for those CPU intensive tasks that are less security sensitive, that you simply will, it's just harder. It's harder to do ASN1 parsing inside of these HSMs, just trust me. So it's just easier to do that in the host. And if you have a situation where it's not security sensitive, it just makes it easier to write a Linux app that does that work. But every time a use case is invoked, the Linux app is invoked, then the module inside the HSM is invoked, and then it goes back to the use case. So you can run Linux code at the beginning, at the end, and in the middle, it transitions to the HSM code. This is custom firmware running inside the secure boundary of a tamper-proof device. So while the Linux application, the use case application, can access unsecured data, just anything that it needs that is available, inside the HSM code, that custom firmware, can access two kinds of secure data: module context and device unique keys and data. Module context is key material that is used over and over again. The same key is used every time the module runs. For example, if we're creating an X509 certificate and you need to sign that certificate, you're signing it with a CA subordinate key that is the same every time. So that key lives in the module context. The device unique keys and data, as the name implies, that's data that is going to be used once and only once for a specific device. That's essentially a database. It's a database of encrypted data. The records are peeled off one by one, decrypted, and packaged up for the provisioning. Now, the reason we built it this way was flexibility. What this allows us to do is reuse that firmware module, for example. If you're building certificates and signing them, you can reuse that signing module over and over and over, and by simply swapping out the module context, you're using a different signing key. So I know that's a lot. The point I really want to make is we have tried to break this down into these fundamental components that we believe create a tremendously flexible system for designing, coding, and running any use case that's thrown at us. Okay, we're getting near the end. In this section, I'm going to talk about what we're working on right now, which is securing the supply chain. You can think of supply chain security as having a couple of different kinds of control. In this picture along the top, we have life cycle state. So you've got a wafer, and then you've got chips, and the chip is put on a board, the board is put in a box, and then the box is distributed to the end customer. At each of those points, there is information on that chip. There are keys, there is life cycle state. All of that can be used to create security. You can have, again, going back to our flagship root of trust product, CMRT, you can have a secure application that will run in the blank state, but will not run in mission mode, and vice versa. You can have equipment that is going to do a challenge response with a key it knows it's going to be there, and only proceed if that challenge response succeeds. This is what we do today. This is what a lot of people do today. For that life cycle state control, to make sure that the things that are happening on this chip are authorized to happen because of what you can test on the chip itself. But what is missing is coordination of all those different points along the supply chain. So what we're building now, which is really an extension of our KMS product, is a system that coordinates data all across the supply chain. So information that is collected at the sorted state, or even created at the sorted state, can be used in mission mode to enhance the ability to authenticate device, to attest that device has not been tampered with, and to ultimately authorize whatever it is you're going to do to this device. So another way to look at that is this slightly more colorful picture. Again, we have our supply chain coordination built from the KMS at the center of it. At the top, we have information that is not coming from the activity that we're managing. We have endorsements. That is a trusted computing group term for a piece of fixed data that you can somehow trust. Think of like the hash of a firmware, for instance. So we have to have a way that you can get a firmware hash so you can verify that the firmware that's running on this device is authorized. That comes in from a third party. We also have entire provenance chains coming in from third parties. When you're out there on that box, we do not make the assumption that every single chip on every single board went through our system. But we do want to absorb all of the provenance data that was collected by other systems and make it part of the final report, the final picture of the security state of this box. So we have ways of securely bringing in endorsements and entire provenance chains. Now, the systems that do interact directly with the supply chain coordinator have a two-way communication. So as I said before, information that is provisioned when, say, the device is a chip and before it's been put on a board, that can be communicated back to the cloud. For example, if you put a device unique key on that chip, that device unique key's value can be communicated to the cloud service, and then later positions on the supply chain can do challenge response or other authentication work or attestation work, knowing not just what this chip looks like in general, but what this chip with this unique ID looks like, exactly the state of one chip, no matter where it is in the supply chain. So when this system is done, we're going to be able to leverage the trusted data from multiple vendors, multiple suppliers, entire provenance chains from other systems like this, bring it all in and incorporate it into one picture. We're also planning to offer ways to measure and quantify the security at each of these stations. Just how secure was it? And then somehow roll all that data up to quantify the security across the supply chain. There is never perfect security, and there is a wide range of systems out there, and different applications need different levels of security. So we're not suggesting that this system is to create maximum security across the supply chain. It is to optimize security across supply chain and quantify what the security is there. So that's where we're heading now. This is not too far in the future. This is where a lot of our work is done. We're going to take a product which is almost 10 years old, our original factory provisioning. We're to take our cloud product, which is about 4 years old, and we're moving both of them into a more robust, wider scale supply chain security solution. That's all I've got. Thank you for coming. And if you'd like more information, please check out our website. Thank you.